Hi class, this video is on topic C7, magnetism. So a magnet produces a magnetic field in the space surrounding it, which causes a magnetic force on a second magnetic object. A magnetic field is referring to the space around a magnet in which a magnetic force can be detected. And field lines indicate the strength and direction of the magnetic force. Sound familiar? Just like gravitational field lines, electric field lines, magnetic field lines. Magnetic force is also a force at a distance, just like these other forces that are in this fields unit. And what are force fields again? They are, the force fields are, exist for the non-contact forces. And these field lines are like a map that describe the force experienced by an object placed at different positions. So for example, we place an object with mass here. The gravitational field lines tell us that the force direction will be towards the center of the Earth and that the strength will not be as strong as if we were closer to the Earth. Likewise with this magnet, the field lines point in the direction that a north magnet would point. So if we are over here, the north magnet would be strongly repelled away from the north pole of a magnet. How do we know the fields exist? I think we use this picture of iron filings on a magnet to show how those field lines were 3D in previous lessons with gravitational and electric force fields. And now we're revisiting them again, just to remind us that fields are in 3 dimensions, and we can model all fields using field lines. Field lines do not cross. The concentration of the field lines indicates the strength of the field in that region, and field lines indicate direction of the force. So with gravitational fields, we had objects with mass creating gravitational fields in the space surrounding it, and the force acting on a second object with mass will always be attractive. A charged object will create an electric field in the space around it. So instead of mass, it was charge. The force acting on a second charged object may be attractive or repulsive. And as we're going through these review slides, the reason why we're going through these and comparing the fields is because that is a major learning goal of this unit, is that you can distinguish between the 3 chapters, and that you can point out all the many similarities that gravitational, electric, and magnetic fields have in common. So we've talked about how electric fields could be attractive or repulsive, but gravitational fields could only be attractive. So for magnetic fields, instead of mass or charge, we have a magnet will create a magnetic field in the space surrounding it. The force acting on the second object may be attractive or repulsive. So this is something that it has in common with the electric field lines. In electric charges, we talked about how in the worksheet, there was talk about the positive and negative charges ratio of the positive and negative charges determine the overall charge of an object. So if you have, so all objects have, matter is all made out of atoms that have electrons and protons, and it's just a matter of whether you have a deficit or an excess of electrons. Only the negative charges could be transferred between objects. Objects may be neutral, positive, or negative. We also talked about in electric charges in that section that charged objects exert forces on one another that obey the following rules called the laws of electric charges. These 3 laws state that like charges repel one another, unlike charges attract one another, and that charged objects attract some neutral objects, which was recapped from grade 9 static electricity. Okay, so for magnets. Magnets are iron ores or alloys that have a certain order to their component atoms. This allows them to exhibit magnetic properties. All magnets have 2 polarities, north and south, and they always occur in pairs. You can see, I guess I should mention, okay, iron is an element in particular whose atomic dipoles or magnetic domains are easily aligned. And we're going to talk about magnetic domains in a moment. But just 2 polarities, you can see if it's a horseshoe magnet, has a positive, a south and a north side. A bar magnet has a distinct south and a north side. These always occur in pairs. The law of magnetic poles, so as compared to the law of electric charges, the law of magnetic poles state magnetic objects exert forces on one another that obey the following rules. 1, like poles repel one another. So like poles, like a north pole and a north pole, will repel one another. South pole and south pole will repel one another. Unlike poles, attract one another. So we can say if this north magnetic pole faces this north magnetic pole, there will be repulsion. On the flip side, if there's a south magnetic pole near a north magnetic pole, there will be attraction. So reviewing fields, we have gravitational fields created by mass, electric fields created by charges, and magnetic fields created by magnets. Magnetic fields, we've stated these things. So just take a look at the diagram, the magnetic field line diagram, and just think about how has that been similar or different to something you've seen before. Pause the video, see if you can flip through notes, see if you can see similarities or differences. And we're going to highlight those as we go along. So here are some rules for the magnetic field lines. Instead of with the electric field line, well, gravitational field lines, we always had them pointing towards the planet or the object with a lot of mass. So always towards the planet. With electric field lines, it always pointed positive to negative. So that epsilon electric field strength, that is a vector quantity and always pointed from positive to negative, the same as the field lines. So here with magnetic field lines, the direction is north to south. North side of the magnet to the south side of the magnet. The lines are most dense at the poles because the strength of the magnetic force is strongest at the poles. Lines never cross. Actually going back to, so number 1, we talked about how that was different with the different fields chapters. Number 2, lines are most dense at the poles. So it has always been true that field line densities indicates the strength of the force. But if you think about it, there wasn't a higher density of the gravitational field lines anywhere in the earth. It's just the closer you are to the earth, the more dense the lines were. That is going to be different when we realize that the gravitational field lines are not the only field lines that you can draw around the earth. You can also draw magnetic field lines. And the North Pole, where Santa is, has magnetic field lines that are higher density than if you were at the equator. So with a bar magnet, if we are close to the North Pole, you have a higher force of repulsion or attraction. Notice these lines never cross. This is the same with all fields line diagrams, gravitational, electric, magnetic. And field lines will not, magnetic field lines will not extend indefinitely as all magnets come in north-south pairs or dipoles. Magnetic field lines form a closed loop. So we tend to think of them as starting from the north and ending in the south. But really, if we look inside the magnet, there is the continuation of this loop, so it's a complete loop. Also notice how the interior field lines run south to north. So outside of the magnet, the direction is north to south. Inside the magnet, the direction is south to north, and they form these closed loops. And it doesn't matter, we always have a north and south end of a magnet. It doesn't matter if we were to chop this in half, this middle of the magnet would, on this side, would turn into south, and this would turn into north. So even if you chop a magnet, it still has a north and south pole. So if we compare so far magnetic versus electric field lines, we know that magnetic field lines always result from a magnetic dipole because the north and pole always exist. But electric fields might result from a single charge. If we don't have a single charge, if we have two, remember the dipole, the electric dipole, this actually looks very similar to an electric dipole with the 2 point charges actually looks very similar to a bar magnet, except with electric field lines, you have lines going from positive to negative, or away from positive and towards negative. And with magnetic field lines, looking at the loops from the outside of the magnet, it looks as if they go from north to south. Magnetic field lines form closed loops, north to south, outside the magnet, south to north, inside the magnet. Electric field lines are radially outwards from positive or radially inwards towards negative. So if we take a look at way out here, we've got like, it's like a star pattern, radially outwards. But if we go way out here, those lines will eventually come back. So with this positive charge, especially if there was no negative charge at all, if we just cut this off, this would go back to being like a star. Lines would radiate outwards. Whereas in this case, you can never have just a north pole of a magnet. It's always the loop. So with magnetic field lines, we can observe magnetic field lines outside a bar magnet, a horseshoe magnet, or around the Earth. And in fact, a compass is a magnetized metal needle mounted in such a way that it can spin freely. Since it can freely spin, we can tell if there's attraction or repulsion between the red or the tip of the compass needle and a pole of a magnet. So the north side of the north was named North Magnet because it pointed towards the North Pole where Santa is. A compass can be used to map the direction of field lines around a magnet or the Earth. And the compass needle will align itself along the direction of the field lines. So you can also think of the field lines as the direction that the north side of the compass will point. So not only could we draw the gravitational field lines, which are radially in towards the Earth, we could also draw these magnetic field lines around the Earth. Earth's magnetic field is a result of the motion of its molten core, and it helps to protect us from solar winds and help us navigate about the planet. A few reasons why these are kind of complicated is because Earth's geographic north is the magnetic south. So you might say, well, if I put a compass here, you said that a compass will point in it's the direction that the north side of the compass points. So if the tip of the compass needle is north, why is it pointing to the North Pole if like charges repel? Like poles repel. So the north end of the compass needle is attracted to up here because it's acting like the south pole of the bar magnet. So Earth's magnetic south pole is Earth's geographic north pole, where Santa is. But it's a little bit more complicated than that. So we've got the geographic north. Geographic north and geographic south have been, defined based on Earth's axis. So Earth spins along this axis. But compared to that axis, the magnetic bar magnet, the poles are tilted. So the poles don't line up. The magnetic pole and the geographic pole don't line up exactly. There's that angle of difference, and this difference is not constant over time or it's based on your location. And then also, if you look over here, you see the full complete loops. But if you look over here, it's like as if you have a compass magnet and looking sort of the angle of that compass needle compared to the surface of the Earth. If you're at the equator, then that line is pretty parallel to the ground, and it's just easily pointing to north, to the geographic North Pole or the magnetic South Pole. But the closer you are to the poles, the more that needle is going to want to push into the ground or out of the ground. So that's why it's a little bit more complicated. Let's look at types of magnets. So different magnetic material, we might have natural magnets that are made out of iron oxides. Ferromagnetic materials are not naturally magnetic, but they can become magnetized when placed in an external magnetic field. So the demonstration here is if I take paper clips in my hand, if I ask you if these paper clips are magnets, they are definitely not permanent magnets, but they're ferromagnetic, because if I take a bar magnet to pick up one paper clip, that paper clip that's attached to the magnet is now a magnet itself. And like a barrel of monkeys, I can have a string of maybe 5 paper clips, and the very end of the last paper clip is going to act as a magnet until some point where the force of gravity is greater. The downwards force of gravity is greater than the upwards magnetic attraction, and the paperclip string chain falls. So the 3 types of magnets, besides having like the natural magnets, which are naturally magnetic, or the ferromagnetics materials which can become, we can also classify the type of magnets in terms of if they'll always act as a magnet or not, not just if it's natural. We've got permanent magnets. So we could have a natural magnet that's a permanent magnet, something mined that's permanently magnetic, or we could create a bar magnet, for example, that's permanently magnetic. So a fridge magnet is permanently magnetic. It retains magnetic properties with or without external magnetic field. Temporary magnets, so paper clips, they perform like a permanent magnet only when there is a magnetic field around. So they lose their magnetism when there's not a magnetic field. And then there's electromagnets. So when we turn on electrical current, so electricity is on, then we have a magnet. We flip the switch, there's no current, and the magnet is off. So you can turn the magnet on or off through electricity. And this is because of that connection between electric force and magnetic force. If you remember the right-hand rules from last year, we are right about to go over that connection between magnetism and electricity. So in terms of explaining magnetism, there's the domain theory of magnetism. And it states that regions exist within ferromagnetic materials. And these regions, or these domains, begin to align when placed in an external magnetic field. The net result is a stronger magnet. So let's say we have a material where the domains are randomly oriented. The vector addition of these randomly oriented domains is 0. So overall, there is no magnetic force. There is no magnetic north pole or south pole. If an external, this is explaining a ferromagnetic material, how can it possibly be sometimes magnetic? So this is your paper clip. Without an external magnetic field, it cannot pick up other magnets. But if we have an externally applied magnetic field, all of those domains align, and it creates, so this is like a tiny north pole pointing that way and a tiny north pole pointing that way, and it's vector addition. So if they're all aligned, we have a strong north pole appear. The strength of the magnet is determined by how well the domains line up. So ferromagnetics, ferromagnets, paramagnets, or no magnet for these. This is like the kind of schematic picture of the domains. Okay, so electromagnets, we zoom into that, and this is a recap from grade 11, but it's really important that you review it. So in grade 11, we learned electromagnetism qualitatively. So you had your right-hand rules, and you learned it without numbers. And the next video is we're gonna do calculations, quantitative electromagnetism. So we really have to review the qualitative stuff and really understand it. So an electric current is capable of creating a magnetic field in the space surrounding it. And Ørsted discovered this. So here's the current carrying wire, and the compass needle will point a different direction if there was current going through it as compared to if the current was off. We can amplify the effect if we wrap the wire around a coil, where the direction of the magnetic field is determined by the right-hand rules. So let's review them. So right-hand rules for a straight conductor, your thumb points in the direction of conventional current, and your curled fingers are in the direction of the magnetic field lines. So this is how it would look. So let's do an example. Determine the direction of the magnetic field for each of the following. Current coming out of the page. So you're going to kind of do like a thumbs up, and then you're going to point your thumb. This means out of the page. So it's like you're looking at the tip of a dart that's coming at you. So you take your thumb and you point it at you. And do you see how your curled index finger, middle finger, ring finger, and pinky are curled in the first case counterclockwise? I was waiting for my animation. It was very slow. So that means if you were to put a compass on the left side, the needle would point down. A compass on the right side, it would point up. If you would put the compass needle here, it would point left. If you put it here, it would point right. So let's try the other one. The current is going into the page. We use an X to show that. I remember that as like the back of an, if you had a bow and arrow and the arrow was heading away from you, you would see the feathers, which kind of form an X. So out of the page, sorry, not out of the page, away from you into the page is an X. So you're gonna take your thumbs up and you're gonna twist at the wrist so that your thumb points to hit the screen. And you notice, now you'd be like looking on your pinky side. Your pinky and all of the other fingers, the bent fingers, are clockwise. So that means if you were to put a compass on this side, it would point down. Compass on this side, it will point up. Compass over here, it will point to the right. Compass over here, point to the left. Okay, so not just the straight conductor, we said we can make that, we can make better use of that magnetic field line, that magnetic field that's created if we use a coil. So here we can increase the strength of the magnetic field by coiling the wire. We can also wrap that coiled wire around a ferromagnetic material such as a soft iron armature. This increases the field strength, and that increase in field strength is measured by the relative permeability of the material. So for a coil, we have right-hand rule number 2. So maybe there's good news, bad news. Maybe the good news first. The good news is it's the exact same thumbs up that you would start with. So your hand doesn't change shape. But the bad news is that your thumb used to be the current, and now your thumb is magnetic north. Your curled fingers used to be the magnetic field lines. Now your curled fingers are the current. So firmly, if you coil your fingers of your right hand around the solenoid is the current carrying coil, the current carrying wire that's in the shape of a coil. And then in the direction of conventional current, because you might say I could wrap it around this way or the other way. But you have to look at where is the battery. Conventional current is positive to negative. So this is the positive terminal of the battery. And you have to use maybe, maybe use your pencil to draw it in, and you'd see that it's twirled like this. It's kind of hard to see in 2 dimensions, but hopefully you are using your right hand right now. Make sure you don't accidentally use your left hand. So take your right hand right now, curl it around the coil, and you'll see your thumb will point to the north side, which in this case, in this diagram, is to the left. So determine the polarity of each of the following, then draw the appropriate magnetic field lines. Well, if this is the positive side of the terminal of the battery, so we're wrapping it like this. So we're going to use our hand to see that the left side is north, the right side is south. And when we draw magnetic field lines, we are going to keep in mind those 3 things. The magnetic field lines go north to south. They're strongest at the poles, and they never cross. So we really want to make sure that you can see a higher density of magnetic field lines near the north and south pole. And then for this one, Just make note, if you're following along with the student notes package, I flipped this diagram just to give us a different answer. If the current is coiled that way, now your thumb will be pointing to the right, which means north is over here. And then you're going to draw magnetic field lines that satisfy those three rules. North is south, more dense near the poles, and do not cross. In grade 12, you really should only draw magnetic field lines that are loops, just for the purpose of really stressing that they're different than electric field lines, which kind of could go off into, well, do go off into infinity. That if you have 1 point charge, it's radially off into infinity or radially from infinity. So I don't love this graphic, but it was a nice graphic without a background, so I used it. But I would connect this over to that one to form a loop. Okay, we can take a look at the field lines and determine whether there is an attractive or repulsive force. So for bar magnets, this might be dead easy. You don't need your field lines rules yet, but what we're going on to, this will come in handy. So the direction of the magnetic force can be determined by the orientation of the field lines relative to each other. So you see how this arrow is pointing down over here, and this one is pointing up. So toward south and away from north, they are opposite field line directions. That is attraction. And over here, you have magnetic field lines that are the same direction, indicating repulsion. So let's try an example. Two current carrying wires are placed beside each other. Which orientation will replace a magnetic field such that the two objects will attract? So I'm gonna think, well, what right-hand rule is this so far? Well, there's no coil, so I'm gonna use right-hand rule number 1. It's for a straight conductor. This is a straight conductor coming out at me. You're gonna do a thumbs up, tilt your thumb towards your eye so that you're looking down into your nail. And then you can see counterclockwise rings, magnetic field lines. On the other one, on this one, you would see clockwise. Over here, we don't have the right magnetic field line orientation to have attraction. We get them both traveling up. Then over here, on this side, it's traveling up, but on this side, it's traveling down. So the magnetic field lines cause attraction. So this is our answer, B. And so that was just what we need to know about magnets in general, and a review of the right-hand rule number 1 and 2. So right-hand rule number 1 for a straight conductor, and right-hand rule number 2 for a solenoid. So please make sure you answer this exit ticket and complete these practice questions as we move on in the magnetism chapter, magnetic fields chapter. Have a great day.